Watch one molecule glow. For about a billionth of a second, a photon hits it, the molecule absorbs the energy, then re-emits a photon at a slightly longer wavelength. That tiny round trip is fluorescence, and it powers everything from microscopy to qPCR to single-molecule biophysics. The Jablonski diagram, drawn by Alexander Jablonski in 1933, organizes the relevant electronic states. S0 is the singlet ground state, S1 is the first excited singlet, T1 is the first triplet, same orbital pattern but with paired electron spins flipped. Each state has vibrational sublevels stacked above it. Step 1. Absorption. A photon of energy h nu absorbed kicks an electron from S0 straight up to a high vibrational level of S1. The molecule is now electronically and vibrationally excited. This is a vertical transition. The nuclei don't move during the femtosecond it takes the electron to jump. Step 2. Vibrational relaxation. In 1 to 10 picoseconds, the molecule sheds the extra vibrational energy as heat to the solvent and drops down the vibrational ladder to V equals 0 of S1. Kasha's rule says emission always comes from V equals 0 of the lowest excited singlet, no matter where you started. Step 3. Fluorescence. From V equals 0 of S1, the electron drops back to S0, releasing a photon h nu emitted. The transition lands on a vibrationally excited level of the ground state, which then relaxes back to V equals 0, losing more heat. 2 heat losses, 1 emitted photon. The result is the Stokes shift. The emitted wavelength is longer, lower energy, than the absorbed wavelength. Stokes saw this in 1852 using quinine sulfate. For fluorescein, it's 25 nanometers, 494 absorption to 519 emission. For GFP, it's 30 nanometers, 488 to 507. How fast is fluorescence? The lifetime tau equals 1 over kF plus k nonradiative, typically 1 to 10 nanoseconds. For organic dyes, fluorescein 4 nanoseconds. GFP 3. Ruthenium polypyridyls can stretch to a microsecond. Tau is measured by time-correlated single-photon counting against a picosecond laser pulse. The quantum yield phi sub f is photons out over photons in, equals kF divided by kF plus k nonradiative. Fluorescein and base, 95%. GFP, 60%. Tryptophan, only 13%. Phi f times molar absorptivity epsilon gives brightness, the real figure of merit when picking a probe. Sometimes the excited singlet doesn't fluoresce. It crosses to the triplet T1 via intersystem crossing, a spin flip. From T1, return to S0 is spin forbidden, so phosphorescence is slow, microseconds to seconds, and even more redshifted than fluorescence. Glow-in-the-dark stars and oxygen sensors live here. Applications. GFP fusion proteins won the 2008 Chemistry Nobel. Single-molecule fluorescence with TIRF or zero-mode waveguides lets you watch one polymerase or one ribosome. qPCR TACMAN probes use a FRET-quenching pair that lights up when polymerase cleaves them. FRET itself rules distances from 1 to 10 nanometers. Photon in, redder photon out, in a billionth of a second. That is fluorescence spectroscopy. A single molecule, 10,000 to 10 million cycles before photobleaching, and the most sensitive analytical readout in chemistry and biology.